Hello students, I am Dr. Nimi Singh. Today I bring you the next learning episode in BSc Forensic Science on behalf of the content writers, myself and Ms. Tholika Banerjee on an important unit of paper Criminalistics, that is examination of glass evidence, and part 1 of that. In this lecture we will be studying about the classification of fractures in glass along with examination of glass at the crime scene. We will also acquaint ourselves with the laboratory examination of glass, that is the density measurements of glass samples, and in the next part we will learn the refractive index measurements and elemental analysis of glass. Finally, we will wind up this module with a conclusion. Dear students, let us have a look at the modules which we are going to learn today. We will learn the classification of fracture in glass, examination of glass at the scene of crime, examination of glass in the laboratory, and in the end we will conclude it. Most of the strength of the glass is in its surface. Glass has very less tensile strength as compared to compressive strength. Therefore, the glass bends to any force when exerted on any one of its surface. However, the glass breaks due to tensile stresses that pulls the surface of the glass apart and hence exceeds the elastic limit. Imperfections, flaws or minor damage in the surface of the glass such as scratches, bruises or etching, which we will call as glass fractures, reduce the tensile strength at those points in the surface and hence reduce its tensile strength completely. The study of glass fractures gives a lot of information about the crime. For example, a fractured window glass will reveal the information that can be related to the force and the direction of an impact, which is useful in further reconstructing the crime scene. When there are a lot of pieces of glass in a sample, it is advised to assemble them to know whether the glass fragments come from one or more than one source, which can further reveal the brand or the pattern of the original object. A glass that has broken while committing a crime shows primarily two kinds of fractures, that is primary or first made fractures and secondary or subsequent fractures. Primary fractures are called radial fractures, while the secondary fractures are called concentric fractures. They look like the spokes of a wheel as they radiate outwards from the point of contact. Concentric fractures form a series of broken circles or arcs around the point of contact. Direction of impact cone. Now, the patterns on the glass fractures can actually reveal the direction of the projectile. The pattern can actually reveal whether the object that caused the fracture was moving at a low pace like a rock or a fast moving bullet, whether it is a thermal stress or an impact. This can really be critically important in reconstructing the crime scene. For example, if a bullet strikes a window and penetrates it, while not completely shattering it, it may leave a hole with surrounding fractures or may not. On the side of impact, the bullet will create a clean hole, while on the opposite side, a cone-shaped corner of the glass is forced out. Thus, visual inspection can reveal the direction of impact. Then comes the glass fractures. Now, depending on whether the fracture is caused by a high velocity projectile or a low velocity projectile, there are different kinds of fractures. First is the radial fracture. Radial fractures are produced on the surface opposite to the one where the force had been applied. When an external force is applied on one side of a glass, then the glass sheet bends away from the force so that the tensile stresses are set up in the opposite surface of the sheet, while the compressive stresses are developed on the surface to which the force has already been applied. If the applied force is so strong to have exceeded the elastic limit, the glass breaks invariably from a point where a tensile stress of sufficient magnitude has developed. In a glass sheet, the primary or the initial rupture, which we call as radial fracture, tends to be star shaped or appears like spokes of a wheel. In other words, it spreads from this point of contact as a series of cracks in a number of random directions. For example, penetration caused in the window by a projectile or a bullet produces a pattern in which crack radiates outwards and encircle the hole. Then comes concentric fractures. Now, if the force continues even after radial fracture, especially when the instrument is either blunt or tapers abruptly, there is a bending movement that causes tensile stresses to develop on the side of the glass to which the force was applied. This leads to a series of cracks known as concentric fractures which connect with the adjacent radial fractures. The concentric fractures form a series of broken circles or arcs around the point of contact. Then comes the broken edges. When there is a cut on the surface placed under tension, the glass may not break squarely across. When a piece of glass is broken by bending from a larger piece, the sharp edge remaining on the larger piece will probably be there on the side to which the force has been applied. Hertzian fracture or cone. Usually, the glass breaks by tension and not by compression. For example, when one pushes window glass, it begins to break from the back side and not from the surface where the force has been applied. It breaks under tension as tensile strength of glass is always less than the compressive strength. As far as the failure of tension is concerned, it is not the only mode for breaking a glass. If this would have been the case, the glass would then be impossible to break as it would be unable to bend and create tensile stress. And there is a second mechanism by means of which the glass may be broken is by the formation of Hertzian cone or a fraction. A Hertzian cone is a cone of force that propagates through a brittle, amorphous or crystalline solid from point of contact like a bullet through glass. This occurs usually during very high energy impact. In such cases of high speed and high energy impact, a compressive stress wave will pass through the glass from the point of impact to the opposite side. Such situation is also referred to as dynamic loading. When a projectile strikes a glass pane, longitudinal compression waves are generated, beginning at the point of impact and then moving outwards in a series of spherical wave fronts which travel with the speed of sound in glass. The wave travels almost 20 times the speed of the bullet fired. When the stress wave arrives at the opposite side of the glass, it is reflected and then becomes a tension wave. Upon striking the impact site, it will be reflected again as a compression wave and again launched towards the opposite side. This interactive process results in the interference of tension waves if they are coincidentally in phase. The amplitude of the waves will be additive and as a result due to the accumulation of tensile strength, it results in the fracture of glass. Thus, a flake of glass is ejected from the opposite side. The largest flakes are at the edge boundary, while successive flakes that are close to the point of application are smaller in size. Glass that has been broken in this fashion results in crater opening away from the direction of origin of space. The direction of crater depends on the speed of propagation of projectile. In case of low velocity projectiles such as pebbles, a crater may be formed on the opposite side of the glass, but with no hole or very small hole. even though the projectile does not pass through the glass. If a projectile approaches in a perpendicular fashion, crater is symmetrical. In case of a very high velocity projectile, such as in case of a rifle bullet, it will yield a small hole with minimum flaking around the circumference. A slow moving bullet, however, delivers more irregular hole with substantially more flaking. If an intermediate target has reduced the velocity of the projectile to even below 200 foot-pounds per second, the glass show evidence of tension which is propagated fracture with no crater formation. Fractures in container glasses. The fracture begins with which we call as fracture origin at a single location. Very rarely, the fracture will traverse the thickness of the glass wall to the opposite surface as well as being propagated away from the fracture origin. The fracture in the containers arises due to the following stress conditions. First is the internal pressure. If a glass container fractures due to excessive internal pressure, the typical fracture appears is a straight vertical split in the side wall of the container, which may be due to the excessive carbon dioxide in beverages, from thermal expansion of liquids, due to heat or generation of gas due to decomposition of contents. It usually originates at the heel or bottom where stresses are greater. These rarely originate in the neck of the bottle, as the neck is stronger than the side wall option. After the initial fracture, it often forks at both ends, producing a series of fractures that are symmetrical about the initial longitudinal fracture, that is, it is in the form of a fan shaped pattern. As a fan shaped pattern diverges, it travels through the circumference and separates the neck and base from the rest of the portion. Then comes the thermal fracture. If very hot liquids are poured in cold glass, a very cold liquid is poured in hot glass, a thermal shock is produced, leading to fractures. These occur in the bottom of the container, around the circumference, with no or very rare surface markings, resulting in fracture along the long axis of the container. Then comes the impact fractures. These generate the most complex stresses of any type of fracture. There are three distinct phases of impact fracture: contact stress, flexure stress and hinge stress, although the actual physical appearance of the fracture will be determined by the one which is dominant. Come to contact stresses. They are nothing but generated at or very close to the point of application of the impact force, resulting in Hertzian fracture or in chips along the mouth of the container. Flexure and hinge stresses, they arise from localized defect on the inside of the glass. A very slight impact would be enough to cause the container to fracture. This will result in a star-like appearance on the inside of the container, while at the same time causing the bending of glass wave to the outside. The stress created by this outward bending is the hinge stress. Hinge stress fractures generally occur at the same height as the initial fracture at about 45 degrees. On examination of fractured glass, different types of markings can be observed, which tells about the direction of the force and the stress on the glass. Depending on whether the hit is a directed, or in other words, whether the force applied is perpendicular to the glass or sideways, that is right to left or left to right, different markings characteristic of a fracture are observed on the glass. This makes the first step in the examination of glass a bit simpler. Rib marks. Now, on examination of the fractured edges, if curved markings like waves are observed, then these markings are what we call as rib markings. The convexity of these marks actually indicates the direction of travel of the bullet. They appear perpendicular to the surface at which the crack originated and then curve asymptotically, that is meeting at infinity with the opposite surface. The direction of travel of the crack along the glass is from the concave side of the rib marks to the convex side. The rib marks being almost at right angles to the face of the glass on which the crack has been opened, it has been observed that on radial fractures the rib marks are perpendicular to the face opposite to which the force has been applied, while on the concentric fractures the rib marks are perpendicular to the face on which the force has been applied. The crack opens on the opposite face to the point of contact. The examination and thus the interpretation of these fractures are used to determine whether a window has been broken from inside or outside. Thus, it is necessary to determine as to which surface of the broken piece of glass under consideration were originally interior or exterior. Rib marks are the most conspicuous of all the glass edge markings, which are curved shell-like marks. These are also called conchoidal marks or Warner lines. We know that a fracture propagates perpendicular to the principal tensile strength, due to which the fractures tend to orient themselves in such a way that they continuously remain perpendicular to the principal tensile stress. So, when examining a radial fracture, the conchoidal lines meet the side which is opposite to the force at nearly right angles and then curve back asymptotically towards the side from which the force was applied, but in concentric fractures the tension is on the surface which is facing the force. So, when the glass breaks due to tensile failure, the fracture is initiated on the side facing the force. The curved rib marks or the conchoidal marks will now meet the side which is the side facing the force at almost right angles. Then comes the hackle markings. Hackle markings are found in that area on the fractured surface where there has been a relatively high stress. These markings actually consist of ridges which are running in the direction of fracture propagation and are at right angles to any rib markings which may be internal. They are most prevalent when the fractured surface runs at an angle of 45 degree to a pre-existing free surface. Thus, hackle markings are a definite indication of the direction of propagation. There are two types of hackle marks: twist hackle. They appear at the region where the tensile stress twisted from crack surface. Twist hackle can be generated by the primary crack as it travels through the body, especially as it goes round the corners, or geometric irregularities, or if the stress conditions change. While mist hackle, they appear around the origin. They are also called velocity hackles. Now, coming to the backward fragmentation. If a glass breaks as a result of mechanical impact, then a large number of small glass particles will be generated and is projected for a considerable distance from breaking point or object. The projection of glass particles back towards a person or object breaking a window is known as backward fragmentation. This is the actual means by which someone who is breaking a window acquires glass particles on his or her clothing. If a glass breaks under thermal shock, then it has an irregular pattern and produces far fewer smaller particles than an impact break. In detail, whenever a sheet of glass is bent so that there is a tensile strain on one surface, there is actually a compressive strain on the other surface. So, when the glass breaks at the surface under tension, the crack travels to the surface under compression, so that the whole compressive force is exerted along the broken edges in contact. This causes flakes to be split off the broken edges of the glass sheet at the compressed surface, and these chips frequently fly off with considerable velocity. Chips from radial fractures come from the side of the glass to which the force was applied and travel in the direction opposite to the force. Coming to the various methods of examination of glass in laboratory. The first is the density measurement of glass samples. Now, the density measurement is one of the most important analysis for comparing the glass samples under investigation. The comparison of densities can give a proof of a connection, if at all, between a suspect and the crime scene. If the density of a sample glass specimen and the one under consideration do not match, then it can be proved that they do not share a common source or region. But if the densities match and it is proved that the origin of the glass specimen is common, then it becomes very easy to trace the type of glass used by the criminal to conduct the crime and can be helpful in leading the forensic expert to the suspect. Now, importance and use of density measurement. Density can be actually useful in knowing the composition of the glass sample, as it is defined as mass per unit volume of the sample. Density, being an intensive property, does not depend on the size of the sample. In other words, it remains the same regardless of the fact whether the sample is big or small, but it depends on the changes in the composition and is measured directly or by comparison. This measurement is used only if elemental analysis is not available. Density measurements should be done for samples more than 2 to 3 millimeter in size. These measurements are useful in identifying multiple sources present in the sample. Now, what are the prerequisites for density measurements? Proper sample, that is the preparation, that is the density measurement will not be appropriate for cracked glass fragments or comparing bulk fragments. The cracks in the glass sample can make the glass appear less dense than it really is. Density measurement and comparison between the known samples and the suspected samples should be done using fragments of equal size. Samples should be clean and dry. Since window glass does not have a uniform density, so care must be taken to determine the variation in the density of the known sample from different locations. Also, the surface of the tempered glass is less dense than its interior, so one has to be careful in taking measurements of several known samples. Now, there are different methods for density measurements. The glass fragments under criminal investigations are very small, and so the density of such fragments can be determined either by flotation method or by density gradient method. Both the methods are based on the fact that the glass fragments will float in a liquid medium having density greater than that of the fragments, while they will sink in a liquid medium having density lesser than the fragments, but they remain suspended in a liquid whose density is same as that of the fragments. These methods are so accurate that they can distinguish glass particles that differ in density by 0.001 grams per cc. For the heavier liquid, bromoform or methylene iodide is used. For lighter liquid, xylene, bromobenzene, benzene or nitrobenzene is used. Heavier liquids. Now, bromoform, chemical symbol CHBr3, it is brominated organic solvent and pale yellow liquid at room temperature. It is high refractive index, very high density, say 2.89 grams per cc, and a sweet odor like chloroform. Methylene iodide, also called iodomethane, this is a chemical compound with symbol CH3I. It has high density, that is 2.28 grams per cc, is colorless and volatile in nature. Coming to lighter liquids, xylene with the chemical symbol CH10. Xylene or dimethylbenzene is an aromatic hydrocarbon mixture containing a benzene ring with 2 methyl groups at various substituted positions. It has a very low density of 0.864 grams per milliliter. Coming to benzene, chemical symbol C6H6. It is an important organic compound. Each molecule is composed of 6 carbon atoms joined in a ring with 1 hydrogen atom attached to each carbon atom. Its density is again very low, 0.876 grams per cc. Then comes the nitrobenzene with the symbol C6H5NO2. It is water insoluble and pale yellow oil with almond like odor, having density of 1.20 grams per cc. It freezes to give greenish yellow crystals. Then comes bromobenzene with the symbol C6H5Br. It is an aryl halide formed by electrophilic aromatic substitution of benzene using bromine. It is clear, colorless or pale yellow liquid with density of 1.5 grams per cc. Now let us come to flotation method. The crime and control glass piece, the one with the known density, samples are crushed to a comparable size with similar shape, which is one of the most important steps. Each piece of glass is briefly sketched and marked for reference. A clean and dry sample of crime glass particle, which is again an important precaution, is placed in a small beaker containing bromofoam. The glass will float on the liquid surface, indicating that the density of the liquid is greater than that of the glass. The less dense liquid xylene is then added slowly, drop by drop, with stirring until the particle is exactly suspended. One should be careful while adding the mixture that it should be stirred with each addition so that the air bubbles, if any, are removed. Added similar sized clean and dry sample of control glass. If both the crime and the control glass particles remain suspended in the liquid, then their densities are equal to each other and to that of the liquid mixture. Particles with different densities will either sink or float depending upon whether they are denser or less dense than the liquid medium. The densities of the particles of the glass can be determined by calculating the density of flotation mixture using densitometer. A portion of the flotation mixture is transferred directly to the densitometer and the density is thus recorded. Then comes the density gradient method. Now, density gradient method is a very good method for examining the glass fragments when there are a large number of glass fragments, that is, several unknown samples or from several possible sources. In this method, a vertical glass tube about 5 millimeter with internal diameter and 10 to 18 inches long is sealed at one end and filled with successive layers of liquid in decreasing density. In other words, the gradient is such that the density at any level is less than the density of any level lower in the tube, but greater than that of any level higher in the tube. The standard gradient tube is made up of layers of two liquids mixed in varying proportions so that each layer has a different density. When completed, a density gradient tube usually has 6 to 8 layers. In this experiment, one can not only compare the glass particles but also calibrate the density column. The first layer is the heavier of the two miscible liquids selected. For example, bromofoam is heavier while bromobenzene is the lighter one. The second layer is a mixture of 3 parts of heavy liquid and 1 part of the light liquid. The third layer consists of equal proportions of both the liquids, while the fourth layer consists of 1 part of the heavier liquid while 3 parts of the lighter one. The fifth layer consists of only light liquid. The layers are added on each other carefully with the help of a pipette to avoid mixture at the interface. The topmost layer and the last layer is taken in such a way that it is about 1/4 to the height of the column, while the second, third and fourth layers are almost about half of the height of the first layer. The last or the top layer is of the same height as the first layer. Care should be taken to keep the gradient tube overnight so that the liquids diffuse into each other to form a gradient. The glass fragments should be carefully and gently placed in the tube and allowed to settle down. These fragments will suspend in the portion having same density. Thus, the density of the liquid and hence of the fragments can be determined. The densities of various glass and related materials are flat window glass 2.47 to 2.56, headlight glass 2.47 to 2.63, mica 2.6 to 3.2, quartz 2.65, flint glass 2.9 to 5.9, diamond 3.01 to 5.2. Glass has less tensile strength as compared to the compressive strength. Therefore, the glass bends to any force when exerted on any one of its surface. The study of glass fractures give a lot of information about the crime. When there are lots of pieces of glass in a sample, it is advised to assemble them to know whether the glass fragments come from one or more than one source, which can reveal the brand or the pattern of the original object. The fractures present help in reconstruction of crime, knowing the direction of impact and about the source of origin also. With all these information, here we come to the end of today's lecture. Do keep in mind what we discussed today. I will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQs, quizzes, LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.